Good evening. My name is Prithvisha Nath. I am a PhD student in the Department of Aerospace Engineering at IIT Madras, and I am the TA for this course, Vibration of Continuous System. We will be solving some questions. So let's start. The equation of motion for axial vibration of a bar is given by the equation of motion for an axial vibration of a bar is given by this equation, where A is the uniform cross-sectional area of the bar. A is the uniform cross-sectional area of the bar. Rho, here M is equals rho into A. The mass M in this equation. So rho is the density of the material. E is the modulus of elasticity. F is the external force. And U is the longitudinal displacement of the bar. And M is the uniform mass of the bar. For free vibration analysis, Fxt is 0. So the equation becomes like this. For free vibration analysis, the equation becomes like this. Now we'll move on to the question. So in the first question, we have to find the natural frequency for torsional vibration of a fixed shaft. So we know the solution can be written like this. Into c cos omega t plus d sin omega t. Now, since it's a fixed bar, we can write this as for the end condition, like for at x equals 0 and time equals t, we can write this equation as so the term containing sine becomes 0, so we can write this as, and the cos term becomes 1, so we are left with a c cos omega t plus d sin omega t. Now from this equation we can say which is equals to 0, we can say a equals 0. Now for the other end that is x equals L, we can write this as d sin omega L by c into c cos omega t plus d sin omega t, which is again equals to 0. Now what can we write from this is sin omega, this implies sin omega L by c equals 0. So this can be written as omega n L by c equals n pi. So from this we can say omega n equals to n pi c by L. Now c is g by rho. Now we can write c as square root of, now in place of c I will write this. So finally the expression of omega n becomes this. Now for the next question, it is asked, find the fundamental frequency for torsional vibration of a shaft of length 2 meter and diameter 50 millimeter when both the ends are fixed. The density of the material is 7800 kg per meter cube and the modulus of rigidity is 0.8 into 10 to the power of 11 Newton per meter square. So here we are given a shaft which has both ends fixed. So in the previous question we derived the condition for the frequency for a fixed shaft, for both ends fixed shaft. So we can use this equation. So what are given? So in the previous question, what was G? In the previous question, G was modulus of rigidity, and rho was mass per unit volume. So we will use this formula for the second question. So what are the things given? Length of the shaft, is L, 2 meter. Diameter of the shaft is 50 millimeters. Density of the material is given as 7,800 kg per meter cube, and the modulus of rigidity that is given to be 0.8 into 10 to the power 11 Newton per meter square. So in this question we are asked to find the fundamental frequency of the torsional vibration. So from previous question we know that omega n equals n pi by L G by rho. So since we are asked to find the fundamental frequency, here n should be 1. So for finding the fundamental frequency, a fundamental mode of vibration, for finding the fundamental frequency, n equals 1 and omega 1 should be pi by L G by rho. Now I substitute the values. L is given as 2 meters. G we know from the question. Divided by 7,800. So this comes to be so this is equals to 5030.6 radians per second. So this is the answer. Now we'll move on to the next question. It says that an external torque is applied at the free end of a fixed free uniform shaft. Find the steady state vibration of the shaft. Now here we are given an external torque at the free end and we are asked to find out the steady state vibration of the shaft. So we know that the equation of the motion is given by this equation. So we can assume the steady state of vibration as this. Let the steady state vibration, so we can write this as theta equals to x cos omega t. Now we have to substitute this in equation 1. So I'll differentiate this equation. Suppose this is equation 2. I will differentiate this. So this becomes minus omega x sine omega t. Again differentiating this with respect to time, minus omega squared x cos omega t. Now I will substitute this in the equation number 1. So this becomes plus omega square x. Now I'll bring this term c square in the denominator. So the equation becomes like this. Therefore we can write the solution as so x becomes a cos omega x by c plus b sine omega x by c. So I can write the x in this term. Now since it is fixed free end, for x equals 0 and for any time t, we can write the equation like this. Theta is 0 for x equals 0 and any time t. theta is 0. So what can I write from this? From this I can say that x at x equals 0 is 0. Therefore, if I substitute x equals 0 in this equation, the cos term becomes 1 and the sine term becomes 0. So I can say a equals 0. Now what happens at the free end? At the free end, an external torque is applied. Therefore, I can write at the free end, I can write it Gj, since it is at free end, I can write it like this: x equals L comma T equals to mt naught cos omega t This can be seen from the question. The external torque is equals to mt naught cos omega t. So at the free end I can write the equation like this. Now I need this partial derivative of theta with respect to x. So how can I get this? I know that theta is x cos omega t. So the partial derivative is I need to differentiate x cos omega t. So I know the expression for x. What is the expression for x? X is given by this equation. Let this be equation number 3. Now I differentiate this equation. Now x is I write x first. X was given as a cos omega x by c plus b sin omega x by c. Now I can differentiate this. So what will I get from this? And I already know A is 0 from this condition. A is 0, so I am left with B sin omega x divided by C. Now if I differentiate this, what do I get? B cos omega x by C into omega C. Now I will substitute this into this equation. So the partial derivative of theta with respect to x becomes cos omega t B into cos omega x by C into omega C. Now I need this partial derivative of theta at x equals L at any time t. So I'll substitute L in place of x. Now at x equals L and time t, this becomes cos omega t into B into cos omega L by C into omega by C. So now I can substitute this in this equation. Now let this equation be number 4. Now substituting in equation 4, how can I write this as Gj omega C cos of omega L by C. Now there is a B also. So B Gj omega by C cos omega L by C into cos omega t. Now this is equals to mt naught cos omega t. That is the external torque. Now I cancel cos term on both sides. So from here what do I get? I get the expression for B. B becomes mt naught divided by mt naught divided by Gj omega So this is my expression for B. So I know A equals 0 and I know the value for B. Now I can just substitute that in the equation for theta. So theta was given as now what is x? X was b sine omega x by c. Now this implies that theta x comma t equals so in place of x I substitute this b sine omega x by c cos omega t. Now I can substitute the value for b which I got here. So this implies that theta x comma t is given by into sine of omega x by c into cos omega t. So this is the final expression for theta. Now moving on to the next question. Derive the frequency equation for a longitudinal vibration of a step bar having two different cross-sectional areas A1 and A2 and over lengths L1 and L2 respectively. Assume fixed V and conditions. So the step bar looks like this. Now suppose this length is L1 and this length is L2. And the cross-sectional area is given as A1 and A2, sorry. So for this case, what I do is I have to write two equations for the two bars respectively. So how can I write this? So U1 x1 comma t can be written as a1. Here omega x1 by c1 plus sine omega x1 divided by c1 into c cos omega t plus d sine omega t. And for the second bar, I can write this as u2 x2 comma t, which is equals to cos omega x2 c2 plus sine. Here this a1 and b1 are constants, and c and d are also constants. b2 sine omega x2 by c2 into c cos omega t plus d sine omega t. So from the given condition, what can we say? For x equals 0 and any time t. Now suppose for x equals 0 and any time t, how can I write this as? The sine term becomes 0. So we can say that a1 is 0. Now again we have another condition that u1 L comma t is equals to u2 0 comma t. Now if I substitute L comma t in the first equation, what do I get? We know that a1 is already 0. So the first equation becomes b1 sine omega L1 by c1. The second part of the equation gets cancelled for both the cases, so I am not writing that. And for the second equation, u2 is 0. u2 at x2 equals 0. This becomes, the sine terms become 0. So we are left with a2. This is another condition. Now we can see from the question that at x1 equals L1 and x2 equals 0, the tensile force is the same. So how can we write this as? A1 E1. Here this A1 is the area for the bar. At L1 comma T equals to A2 E2 at 0 comma t. So I have to find the partial derivative of u1 with respect to x1. So what was u1? u1 was b1 cos b1 sin omega x1 c1 into c cos omega t plus d sin omega t. Now if I differentiate this with respect to x1, I get this as cos omega x1 c1 into omega y c1 into c cos omega t plus d sin omega t. Now for the what can we write for at L comma T? We can write this as at L1 comma T. We can write this as cos omega L1 C1 omega C1 c cos omega t plus d sin omega t. Similarly, we can do this for the second bar. Now u2 is x2 comma t a2 cos omega x2 by c2 plus b2 sin omega x2 c2 into c cos omega t plus d sin omega t. Now I will differentiate this with respect to x2. So I get this as minus a2 sine of omega x2 by c2 into omega C2 plus B2 into omega by C2 into cos of omega x2 by C2, and this thing multiplied by C cos omega t plus d sine omega t. Now we need to find this at 0 comma t. So at 0 comma t, 0 comma t, we can write this as, in place of x2 I will put 0. So the sine term in this equation becomes 0. So what am I left with? B2 omega by C2 into C cos omega t plus d sine omega t. Now I have to substitute this in this equation. So substituting in equation 1, substituting in equation 1, what do I get? A1 E1 into B1 cos omega L1 C1 into omega by C1. The last two terms already gets cancelled, so I'm not writing this. This term already, C cos omega t plus d sine omega t, gets cancelled in, it is there in both the equations, so it gets cancelled. So I'm not writing this. Equals to A2 E2 omega B2 omega divided by C2. So this is the equation which I get. Now what can I write? I can write B2 in terms of B1. So I can write B2 in terms of B1. So this becomes A1 E1 A1 E1 C2 divided by A2 E2 C1 cos of omega L1 by C1 into B1. So this is my B2 in terms of B1. Now what I will do is write U2. U2 is U2 x2 comma t. This was equals to what was my U2? U2 is this expression A2 cos omega x2 by C2 plus B2 sin omega x2 C2 into C cos omega t plus D sin omega t. So I know A2, I know B2 in terms of B1. So I can substitute this. First I will write down A2 U2's expression again. U2 was A2 cos omega x2 C2 plus B2 sin omega x2 C2 multiplied by C cos omega t plus D sin omega t. Now I know what is A2. I'll write the expression for A2. A2 is B1 sin omega L1 C1 and B1 is I know B2 in terms of B1 I know, and B2 is, I'll write it again, A1 E1 C2 A2 E2 C1 cos omega L C1 B1 till now. Now I will substitute this in this equation. So the my U2's equation becomes sin omega L1 C1 cos omega x2 by C2 plus in place of this constant I will substitute A1 E1 C2 divided by A2 E2 C1 cos of omega L1 C1 into this. So I can take common and the last part is also left, cos c cos omega t plus d sin omega t. So I'm taking common. Sin omega L1 C1 cos omega X2 C2 plus after taking common, I can write this as sin omega L1 C1 into cos of omega X2 C2 plus A1 E1 C2 A2 A2 E2 C1 A2 E2 C1 cos of cos of omega L1 C1 this term also has a sin omega x, yeah, this term has a sin omega x2 term. uh, B1 tilde into sin of omega x2 C2 and then whole multiplied by c cos omega t plus d sin omega t. Now this, then I can take b1 common. So ux2 comma t becomes b1 tilde. I put this tilde to differentiate between the area a1 and a2. These are constants. b1 tilde I can write this as sine omega L1 C1 cos of omega x2 C2 plus A1 E1 C2 A2 E2 C1 cos omega L1 by C1 sine omega x2 divided by C2 whole multiplied by C cos omega t plus d sine omega t. Now I differentiate this. The partial derivative of u2 with respect to x2 becomes b1 omega, I am taking common, b1 tilde omega by c2 omega by c2 I am taking common. So this becomes minus of sine omega L1 C1 into sine of omega x2 divided by C2 plus A1 E1 C2 divided by A2 E2 C1 into cos omega L1 divided by C1 into cos of omega x2 by C2 whole multiplied by C cos omega t plus d sine omega t. Now this has to be calculated for x2 equals L2 at time t. So this partial derivative is 0 at x2 equals to L2 and time t, at any time t. So how can I write this as? L2 comma t equals 0. So b1 tilde omega divided by c2, I substitute L2 in place of x2, so this becomes sine of omega L1 C1 sine of omega L2 C2 plus A1 E1 C2 divided by A2 E2 C1 cos of omega L1 by C1 into cos of omega L2 by C2 . This equals 0. Now I will rearrange this equation. So sine of, and there is a const this term also, c cos omega t plus d sine omega t. This is equals to 0. Now I can say that the term in bracket, the terms in the first bracket should be 0. So sine of omega L1 C1 into sine of omega L2 C2 equals to A1 E1 C2 divided by A2 E2 C1 cos of omega L1 by C1 into cos of omega L2 by C2. I can write like this. So if I further rearrange these terms, this becomes sine of omega L1 by C1 into sine of omega L2 divided by C2 . Here A1 and A1, A2, these are areas. These A1, A2 are area of cross section of the bar. These are different from the constant with the tilde terms. So I write it as cos divided by cos of omega L1 by C1 cos of omega L2 C2 equals to A1 E1 C2 divided by A2 E2 by C1. Finally, I can write this as tan of omega L1 by C1 tan of omega L2 by C2 equals A1 E1 C2 divided by A2 E2 C1. So this is the final equation which I have. Now what I can do is, let me explain this from the beginning. So for the first question, what we did is find the natural frequencies for the torsional vibration of a fixed shaft. So we know that theta can be written like this. Theta equals to A cos omega x. Theta equals to A cos omega x plus B sin omega x by C. A cos omega x by C plus B sin omega x by C whole multiplied by C omega t plus D sin C cos omega t plus D sin omega t. So for x equals 0 and time equals t, so theta is here, theta is a function of x and t. Theta is a function of x and t. So in place of x, if I put 0, the sign terms become 0, and only for the left bracket, first bracket, only a is there. So from so this implies that a equals 0. Now since it's a fixed bar, at end L also theta should be 0. So for theta at L comma t, we can write this as, since a is 0, the first term in the first bracket is 0, we can write B sin omega L by C whole multiplied by C cos omega d plus D sin omega t equals 0. Now from this equation we can say sin omega L by C equals 0. Now this implies that for omega n L by C equals n pi. Now in place of C, omega L by C, omega n L by C. So in place of C, I can write square root of G by rho. This is not, this is rho. G by rho. So finally omega n turns out to be n pi divided by L square root of G by rho. For the second question, we have to find the fundamental frequency for torsional vibration of shaft of length 2 meter and diameter 50 millimeter when both the ends are fixed. Here also we need to find the frequency for fixed end shafts, and the density of the shaft, density of the material of the shaft is given to be 7800 kg per meter cube, and the modulus of rigidity is 0.8 into 10 to the power 11 Newton per meter square. So we know that the length of the shaft is 2 meters, diameter of the shaft is 50 millimeter, density of the material is 7800 kg per meter cube, and modulus of rigidity is 0.8 into 10 to the power 11 Newton per meter square. So from the first question we derived the expression for omega n. From there This expression we already know from first question. So we can use this to find the fundamental frequency. Fundamental frequency corresponds to n equals 1. So in this equation, I put n equals 1. So omega 1 becomes pi by L square root of G by rho. So in place of L I put 2. In place of G and rho I put the values. So this turns out to be 5030.6 radians per second. For the next question, it is said that an external torque Mt is applied at the free end of a fixed free uniform shaft. Find the steady state vibration of this shaft. So in this question, the shaft is a fixed free shaft. That is, one end is fixed and one end is free. Now we can write the equation of motion to be this. So for steady state of vibration, we can assume theta to be x cos omega t, where capital X is a function of small x. Now I differentiate theta with respect to time, which gives minus omega x sine omega t, and I further differentiate, so this comes out to be minus omega squared x cos omega t Now I substituting this in equation 1, we get this. So I divide this c square and the final equation becomes like this. So x can be written as a cos omega x divided by c plus b sin omega x by c. Now we need to find this constants a and b. We know that one end is fixed and one end is free. So for the fixed end at x equals 0 and at any time t theta equals 0. So this implies that a becomes 0. Now at the free end, the external torque is applied. Now we write Gj into the partial derivative of theta with respect to x equals to mt naught cos omega t. That is the external moment, external torque. That is the external torque. So since I assume theta to be x cos omega t, I again differentiate this. Now I know the equation for x, which we got in equation number 3. X was a cos omega x plus b sin omega x by c. Now a is 0, so x is b sin omega x plus c. Now I differentiate this with respect to x, with respect to small x. So this becomes b cos omega x by c into omega by c. So finally I substitute this in the expression of partial derivative of theta with respect to x, which turns out to be cos omega t, and in place of derivative of x, I substitute b cos omega x c into omega c. So what we have to do? We have to calculate this at x equals L and any time t. So in place of x I substitute L. This becomes cos omega t b into cos omega L by c into omega by c. Now I substitute this entire expression into equation number 4, this equation. So this becomes b into gj omega by c cos of omega L by c into cos omega t, and that is equal to mt naught cos omega t. So I rearrange this equation to find b, which turns out to be mt naught into c divided by gj into omega into this term. So now I know the value for b. So finally I substitute all these expressions to get the value of theta as mt naught into c divided by j omega sec omega L by c sine of omega x by c into cos omega t. So this is the final expression for theta. Now the next question, what we had to do, we had to find the frequency equation for the longitudinal vibration of the step bar having two different cross-sectional areas A1 and A2 and lengths L1 and N2 respectively. We assumed fixed free end condition, that is one end is fixed and one end is free. Now we considered two separate equations for the two bars. One is U1, one is for U1 and another one is for U2. So U1 we considered as A1 tilde cos omega x C1 plus B1 tilde sin omega x1 C1 whole multiplied by C cos omega t into D sin omega t. And for U2 it is A2 cos omega x2 C2 plus A2 tilde. Here A1 and A2, that is the symbols without tilde, are cross sectional areas, and A1 tilde and A2 tilde are constants. So for U2, A2 tilde cos omega x2 divided by C2 plus B2 tilde sin omega x2 C2 into C cos omega t plus D sin omega t. Now for U1 at x1 equals 0 at any time t equals 0. So if we substitute that, we get A1 tilde to be 0. Similarly, at x1 equals L and time t equals U2 x to 0 at time t. So from this condition, what we can say is, after substituting x1 as L and x2 as 0 in these two above equations, what we can say is B1 sin omega L1 C1 equals A2. In place of x2, if we substitute 0, we get a2. Only a2. So this is another condition which we get. Again, there is another condition. a1 e1 partial derivative of u1 with respect to x1 is equal to a2 e2 partial derivative of u2 with respect to x2. So I found out the expression for partial derivative of u1 with respect to x1. This turns out to be, if I differentiate, this turns out to be b1 cos omega x1 by c1 into omega c1, and the second term is a constant term. Now at L1 and T1, so I substitute L1 and L1 in place of x1. So this comes out to be b1 cos omega L1 c1 into omega c1, then the constant term, since we are differentiating with respect to x1. Similarly, with the expression for u2, what we do, u2 x2 comma t, we differentiate this. First term is minus of a2 or tilde sine omega x2 c2 into omega c2 plus b2 tilde omega divided by c2 cos omega x2 by c2, and then the constant term. Similarly, here also for x2 we substitute 0. Now this is the final equation. Now I substitute all these things in equation number 1. That is this equation. So finally I get a relation between b2 tilde and b1 tilde, which is this equation. Now I substitute all these values for a2 till a2. I substitute all these values for a2. This is a2 tilde and b2 tilde. I substitute all these values in this equation for u2. So this is the final equation which I get after substituting. Now again I differentiate this u2 expression with respect to x2. So this is the final equation which I get after differentiating. This should be equal to 0. Now finally, after rearranging all the terms, I get the expression as tan omega L1 C1 into tan omega L2 C2 into A1 E1 C2 divided by A2 E2 into C1. So this is the final equation which we get. So these are the questions for this week. So we will stop here.